All right, let's dive right in today. We're going to break down one of the most powerful and maybe a little unappreciated tools in all of computing. The array. Seriously, if you've ever scrolled through your contacts or even just looked at a spreadsheet, you've used an array. So let's pull back the curtain and see how they really work. Okay, so let me start with a question for you. What in the world could a simple plastic pill organizer, the one for your vitamins, possibly have in common with a multi-million-dollar supercomputer? The answer? Well, it's actually way more important than you think. And the answer is organization. They both hinge on this really simple but brilliant idea. A perfect row of numbered boxes all lined up. This whole concept of predictable side-by-side storage. That's the heart of how an array works, and it's the real secret behind its incredible speed. So with that picture in our minds, let's look at the official blueprint. What are the rules? What actually defines an array and gives it all that power? Whoa, okay, that is a mouthful. I get it. Contiguous, homogeneous, index-based. It sounds super complicated, but trust me, don't worry. We're going to break down each of these fancy words, and you'll see it's actually shockingly simple. First up, contiguous. All this means is that everything is stored together shoulder to shoulder and one unbroken line in the computer's memory. Just think back to that pill organizer. The Monday slot is right next to Tuesday, which is right next to Wednesday. No gaps, no exceptions. This perfect nearness is absolutely crucial. Next up, homogeneous. This is another simple one. It just means that every slot in the array has to hold the exact same type of thing. So if you're storing numbers, they all have to be numbers. If it's text, it's all text. You can't mix a number in here and a word and there. It's like a pill organizer, just for your vitamin C pills, not for your entire medicine cabinet. Finally, we have index-based now. This is the secret sauce. Every single slot gets a unique number, its address, which we call an index. And here's the key thing. In programming, we always start counting from 0. So the very first item is at index 0, the second is at index 1, and so on. This is how the computer finds anything instantly. And this little formula, you can think of it as the computer's own internal GPS. Because every item is the same size and they're all lined up perfectly, the computer doesn't have to search around. It can calculate the exact memory address. With this tiny bit of math, it just takes the starting point, adds a little offset for the item you want, and bam, it jumps right there. That's it. That's the magic behind an AR-raised speed. So now we see how all these rules, contiguous, homogeneous, index-based, all come together to give the array its superpower. Because really, when we're talking about arrays, speed is the name of the game. And in computer science, this is what that speed looks like. O of 1. You might hear it called big O of 1, but all it really means is constant time, or even better, instant access. It literally doesn't matter if your array has 10 things in it or 10 million. Getting the fifth item takes the exact same ridiculously small amount of time as getting the 5 millionth item. It's instantaneous. So why should you care about this? Well, this one instant access is why arrays are the bedrock, the foundation for so many other data structures. And because all that data is in one neat block, the computer's processor can grab huge chunks of it all at once, which is incredibly efficient. We call that cache-friendly, and it's the reason your games load fast and your apps feel snappy and responsive. But of course, like any good superpower, this incredible speed comes at a price. It has a weakness, this perfect rigid organization. It has a downside. So let's talk about the trade-off. You can really see that. Side-by-side property right here. Let's say our first number is at memory address 1000, and each number takes up 4 bytes of space. Well, the next one is guaranteed to be at 1004, and the next at 1008. It's perfectly predictable, but you can probably see the problem. It's also completely inflexible. There's no wiggle room. So here's the bottom line, the big trade-off. You always have to remember, arrays give you lightning-fast access, but they are painfully slow. If you need to add or remove things from the middle, that same rigid structure that makes them so fast to read from is exactly what makes them so slow to change. Just imagine this. You've got a big full array. Now you need to insert a new number right at the very beginning at index 0. What do you have to do? You can't just plop it in there. You have to take every single other element and shift it one spot to the right to make room. If you have 1,000,000 items, that's 1,000,000 shifts. It is a massive, time-consuming operation. Okay, so that's a pretty big problem. How do we get around it? Well, programmers have a couple of tools to deal with this, which brings us to the two main flavors of arrays, static and dynamic. It's all about choosing the right tool for the job. On one hand, you have the static array. This is the classic we've been talking about. Its size is set in stone the moment you create it. It's simple, it's predictable, and it's wicked fast. On the other hand, you have the dynamic array. It's way more flexible. It can actually grow or shrink while your program is running. Now, that flexibility has a tiny performance cost, but it's absolutely essential when you just don't know how much stuff you're going to need to store ahead of time. And in most modern programming languages, you don't have to worry about the messy details too much. In C++, for example, there's something called a vector. It's basically a smart, dynamic array that gives you all the power, but it handles all that, resizing stuff for you automatically behind the scenes. And that really brings us full circle, doesn't it? The erase speed is amazing, it's undeniable, but it's built on this rigid, inflexible foundation. So what do you do when you need that speed, but you have no idea how big your list is going to get? What if it's constantly changing? Well, that's exactly why other data structures were invented, and it's the perfect place to leave things for now.